Okay, we are back again. So, this looks like little bit funny, no? But question is that it is something like this. So, actually we know that your omega r, delta omega r is equal to this, we have seen earlier, omega r minus omega 0, right? This we know. So, what you do, you put here that delta omega r is equal to omega r minus omega 0. So, if you do so, it will be writing over it, just see that it is omega r minus omega 0, this term is equal to 1 upon 2 h, right. In bracket it is T m minus T e minus your K d into your omega r minus omega 0, right. Actually it is K d into omega r minus omega 0. Now, if you take the small perturbation on both sides, then what will happen? Then it will be p into delta omega r, then this is your reference speed omega 0. So, p into delta omega r is equal to, it will be 1 upon 2 h, right, and it will be delta T m, just writing over it, just have a look, then it will be delta T e, and again it will be minus K d, and it is omega r minus omega 0, it takes a small perturbation into K d delta omega r, right. So, that is why this T m and T, it is becoming delta T m minus delta T, other things remain same in that equation. So, this is the your only thing is that the delta omega r is equal to omega r minus omega 0, right. So, that is why this equation is written like this, right. Similarly, next page we will see, but I am making it here, just hold on. Similarly, this is nothing for you. Similarly, equation 225, it is p delta delta, p delta. So, p delta is nothing but this is omega 0 and delta omega r actually omega r minus omega 0, right. Now, if you take small perturbation, so it will be p delta delta is equal to omega 0, then delta omega r. So, p delta delta will be omega 0 delta omega r, because this is omega r, this is nothing minus omega 0, right. So, if you take small perturbation, so p delta delta is omega 0, that means this equation can be written as left hand side only p delta delta, right hand side remain as it is omega 0 into delta omega r, right. So, there is no confusion at all from this law, from this mathematical relationship it is coming, right. So, absolutely no confusion, right. So, this is my equation 20 to 25 now, where delta omega r is the power unit speed deviation, delta is the angle in electrical radian per second, and omega 0 is the base rotor electrical speed in radian per second, and p is the differential operator that later we will replace p by s, that Laplace operator, right, and t in second. Now, equation 224 can be written as that p, that what I wrote, p delta omega r is equal to 1 upon 2 h delta T m minus delta T minus delta omega r, this I have explained already. Therefore, p delta omega r is equal to 1 upon T h minus delta T m, delta T we are representing your K s delta delta, that means this equation, this equation later has been explained, this equation can be written as it is K s into delta delta, right. So, that is my delta T e, and this K s is called synchronizing torque coefficient, Why it is called synchronizing torque coefficient? There is a question to you, right. Book you may not find it, but you have to, when you listen this thing, you just put this answer to the forum, right. This term is called synchronizing torque coefficient, right, and it is K s delta delta. So, in that equation we replace delta T by K s delta delta, right. So, therefore, delta T is K s delta delta and minus K d into delta omega. This is equation 220. Forget about this one. This is for my own reference, where K s is the synchronizing torque coefficient, and this K s I told you is nothing but E dash E b upon x t cos delta 0. This is equation 227, right. Now, equation 224 I told you can be written as, I told you already, I told you that it was p delta is equal to omega 0 delta omega, then again p delta delta also will be omega 0 delta omega. This already I have told you previous page, right, just previous page, from that only, that is equation 224 how it is coming, right. Therefore, equation 226 and 228 can be written in that your state variable form. that is your P is nothing but d dt, that is basically delta omega r, I mean d dt of delta omega r means delta omega r dot, and d dt of delta means that delta means delta dot. You put this equation 226 and 228 in the matrix form, then it will become state variable form. It will become that it is 2 into 2 matrix, but slowly and slowly dimension we will consider other thing. So, dimension of the matrix will grow slowly and slowly. So, in this case it is minus k d upon 2 h, this is minus k s upon 2 h, this is omega 0 and this is 0, this is delta omega r, this is delta plus 1 upon 2 h and 0, this is delta T m. So, basically your P delta omega r is equal to minus k d upon 2 h delta omega r that we have seen, and minus k s upon 2 h delta plus 1 upon 2 h delta T m. Similarly, delta is equal to omega 0 delta omega r, right, and this is delta omega delta, this is delta T m. This is equation 229, right. This equation can be written as x dot is equal to a x plus b u. That means your x is actually, this is your A matrix, right, this is A matrix, it is a 2 into 2 matrix, right, and this is your B and this is your u. So, actually u here is just we have represented like this, u is equal to delta T m, right, and this is my B matrix, and this is and state variable, that is x dot is equal, that means x 1 is equal to here delta omega r, and x 2 will be is equal to delta, right, and this is my state variable equation. Now, if you represent this in block diagram, then this is my delta T m, right, and if you look into this, just see those equations and construct the block diagram. This is delta T m and this is minus delta T e, right. So, we have seen, no, and this is your delta omega r. So, k d delta, that is delta T m minus k s delta T e minus your what you call k d delta omega r, right, into 1 upon 2 h s is equal to delta omega r. This we have seen, right, and this is your, and that is also you have seen from the second equation, that is I think 226. I think this is 228, this is 228, it is 228 is P delta is equal to your omega 0 delta omega r, right. So, when you are putting this in Laplace transform, actually P is represented by S, right, I mean this one now P actually you replace by S. Therefore, this equation instead of instead of S delta S, then delta omega S, we are not representing, it is understandable, only P is replaced by S. So, this is S delta is equal to omega 0 delta omega r, right. That means I am putting it here, that means my delta this one is equal to your omega 0 by S, right, into delta omega r, right. So, omega 0 by S delta is equal to into delta omega r. That is why your your what you call it is delta is equal to omega 0 by S into delta omega r. Similarly, here also that your 2 h s, that P first equation, that is your equation your 226, right. So, this equation also you replace by your what you call that P is equal to S, right, P is equal to d dt, just 1 or 2 lines I am writing for you, it is P is equal to you replace P by S, we will go to the Laplace domain, right. So, that means this is my S and this is delta omega r is equal to 1 upon 2 h in bracket delta T m minus delta T minus your K s delta then minus K d delta omega r, right. So, what you do, multiply cross multiply, that will be 2 h s delta omega r, bring this term to this side, so it will be plus K d delta omega r. So, take omega r common, it will be 2 h s plus K d, right. So, based on that only your this thing is coming, right, this thing is coming, that is your block diagram, this one is coming 1 upon 1 upon 2 h s, and this is your feedback is taken, that is your K d, right, that this one coming like this. So, in this case later we will see, in this case your omega r, this K d omega r term, it did not bring to the your left hand side, only simply we have taken S delta omega r, I mean it is simply like this. Later we will bring it this to that side, if you replace P is equal to S, say P is equal to S, then your delta omega r is equal to 1 upon 2 H s, right, and in bracket it is delta T m minus K s delta delta minus K d your delta omega r, right. This is taken, but delta omega r we did not bring it to the left hand side. Later you will see when block diagram will slowly will grow, and your number or your order of the equation will increase. At that time we will bring this one to this side, at that time we will find it will be 2 H s plus K d omega r will represent step by step, right. So, this is 1 upon 2 H s and this one, right. So, that is why this one, this equation, this block diagram is like this, right. It is your 1 upon 2 H s, right, into your delta T m minus your K s delta delta minus K d delta omega r, right, is equal to delta omega r, and this is I told you that delta delta is equal to omega 0 upon s your delta omega r. Now, this is the block diagram of a single machine infinite nervous system with classical generator model. Now, next is from figure 25, I mean from this figure you just simplify this one, then because if I just I am telling how to do is that delta delta is equal to omega 0 upon s, delta delta is equal to omega 0 upon s into delta omega r, and delta omega r is equal to 1 upon 2 H s, delta omega r is equal to 1 upon 2 H s that we have seen into delta T m minus K s delta delta minus K d delta omega r. So, that is delta delta is equal to omega 0 upon s into 1 upon 2 s minus all these things, right. Now, or delta delta is equal to omega 0 upon s 1 upon 2 H s that minus K s delta, and this delta omega r you replace delta omega r is equal to your s delta delta upon omega 0, because here from here your I am writing here, just hold on, from here that delta delta is equal to omega 0 by s into delta omega r, right. Therefore, delta omega r is equal to s by omega 0 into delta delta, right. So, this delta omega r is equal to s by omega 0 delta delta, you substitute. So, if you do so, it is coming delta omega is equal to K d minus K d s delta delta upon omega 0 plus delta T m, right. This is equation 230. This right hand side whatever is written, this is for my own reference. So, now if you simplify this one, cross multiplication and simplify, then it will be coming like this, a square delta delta plus K d upon 2 H s into delta delta plus K s upon 2 H omega 0 delta delta is equal to omega 0 upon 2 H delta T m, right. This is a simple quadratic equation and characteristic equation, right. That is you have studied also in your third year control system engineering. Therefore, the characteristic equation is given by second order system, it is a square plus K d upon 2 H into s plus K s omega 0 upon 2 H is equal to 0. This is equation 231, right. So, this is the simple second order equation, right, characteristic equation. So, equation 231 is of the general form you have studied in your third year control system engineering. For second order system it is a square plus 2 xi omega n s, right, plus omega n square is equal to 0, right. Therefore, omega n square your is equal to, I mean this is this equation and this they are analogous to each other. Therefore, omega n square is equal to K s just let me delete it once again. So, these two equations are analogous to each other. Therefore, omega n square is equal to this one your K s omega 0 by 2 h, right. Therefore, omega n is equal to root over K s omega 0 upon 2 h, that is here radian per second, omega n is equal to root over K s upon omega 0 2 h. This is equation 233. This is nothing, this is for my own reference, right. So, this is radian, that is omega n, right. Another thing is that 2 xi omega n, let me clear it. Another thing is that this term is analogous to this term is equal to this one, that means 2 xi omega n is equal to K d upon 2 h, right. So, from which omega n is known, and if you substitute omega n you will get this value of xi, right, that I have written in the next line. So, and that is the xi is that is the damping ratio, that is xi is equal to half into kd upon 2h omega n, right. So, therefore, the undamped natural frequency is omega n is this one, right, and the damping ratio xi is half into kd upon 2h omega n. Now, put omega n value and simplify, you will get xi is equal to half kd root over 2h ks omega 0. This is equation 234. Forget about this one, this is for my own reference. As the synchronizing torque coefficient, that is your ks, increases, the natural frequency increases and the damping ratio decreases. That as ks increases, natural frequency your increases, because this is actually omega n root over ks into omega 0 to h. If ks increases, then omega n natural frequency also increases, and in the damping ratio case, ks term is root over 2h ks omega 0, it is in the denominator. So, if ks increases, that xi decreases, right, that the damping ratio decreases, and increase in damping torque coefficient kd increases the damping ratio. Now, kd is in the numerator, if kd increases, the damping ratio increases, right, whereas an increase in inertia constant decreases both omega n and xi, right. So, if h is in the your denominator, h increases means xi will decrease, right. Similarly, here also it is in the root over ks omega 0 upon 2h. So, h in the denominator. So, if h increases, so natural frequency will decrease, right. So, next is that effect of, I think this block diagram is understandable to you, later we will take some problem later, right. So, next is effect of synchronous machines field circuit dynamics. So, now consider the system performance including the effect of field flux variation. Now, we will effect of synchronous machine field circuit dynamics. All these equations for field circuit, everything has been developed before. So, what I will suggest that again and again I cannot go back to those equations which I have left much before. So, whenever you will listening to this lecture, just open those notes, because all notes you every week you will get those notes, keep it in front of you, then things will be easier. Now, consider the system performance including the effect of field flux variation. The Emerson effects will be neglected just for the simplicity and the analysis, because we will think about the classroom exercise. So, will be neglected, and the field voltage will be assumed constant, that is the manual excitation system. We will assume the field voltage will remain constant. Regarding excitation system, I told you if time permits, at the end I will try, but if time does not permit, it will be impossible, right. So, Emerson effects will be neglected and the field voltage will assume that is constant, that is EFD. If it is constant, that means your perturbation delta EFD will be 0, right. So, synchronous machine equations, this all the now, and in the case of the classical generator model, the acceleration equations are, we have seen that P delta omega r is equal to 1 upon 2h Tm minus T minus Kd delta omega r, and P delta delta omega 0 delta omega r, or in other way small perturbation, when you see P delta omega r upon 1 upon 2h, we have seen delta Tm minus delta T minus Kd delta omega r, and P delta delta will be omega 0 delta omega r, right. Now, omega 0 is equal to 2 pi f0 electrical radian per second, that is your base speed, right. Now, in this case, the rotor angle delta is the angle, that is electrical radian per second, by the q axis lead the reference voltage EB, that also we have seen, right. As shown in figure 26, the rotor angle delta is the sum of the internal angle delta I and the angle by which it leads EB. So, before going to this, I will go to this figure, this is figure 26, this is my EB, say, right, this is my EB, this is the reference you have taken, and this is your q axis and this is d axis. So, on the q axis it will be EBQ, that is capital EBQ, and on the d axis it will be capital EBD, right, and this is my ET, that is your that is a terminal voltage ET, this is ET, I hope it is readable, right, this is my ET, this is ET, and this is the phasor diagram, and it's your on q axis component is EQ and d axis component is ED, and ET, this ET actually you are lagging from this EQ or capital EBQ by your this thing by an angle delta I. This also you have seen earlier, and this is the delta. Delta is equal to the delta I plus the angle between ET and EB. But delta is equal to delta I, this angle plus angle between ET and EB, right. So I will go back again. So this is what I told in that is figure 26. The rotor angle delta is the sum of the internal angle delta I just told you and the angle by which ET leads EB. Now we need a conventional means of identifying the rotor position with respect to the appropriate reference and keeping track of it as the rotor oscillates, right. So choice of EB as the reference for measuring the rotor angle is convenient from the viewpoint of solution of network equation. So EB we have taken as a reference, right, and delta will be delta I plus the angle between ET and EB, right. So from equation 121, right, all these equations have been given before. You go to equation 121 with time t in second instead of per unit, the field circuit dynamic equation can be given as your P psi FD omega 0 EFD minus RFD ID. This is from equation 121. I suggest that all the lecture notes will be available to you, just to open it in front of you, because if I want to go back to equation 121 then much time will be lost, right. So or this EFD also we have multiply omega 0 and EFD also defined before, you put it here, right. So it will be, and whenever using U and S, U means unsaturated value and S means saturated value with the inductance or reactance when you are putting, right. So P psi FD is equal to omega 0 RFD upon LADU EFD minus omega 0 RFD IFD. This is equation 237, right. So now with the Emerson's neglected, the stator flux linkage are given by that go back to the stator circuit equation, right. This equation, if I recall correctly, you go to the figure 20A, right. So from figure 20A, that where analogous circuit is given flux, then your inductance, then your what you call that your current, right. So with Emerson's neglected, the stator flux linkages are given by this. You go to figure 20, which you have left out, which you have left before, right. So it will be minus LLID plus LADS in bracket minus ID plus IFD, right, or psi d is equal to minus LLID plus psi AD. Psi AD is equal to this term. This go back to figure 20A. If I recall correctly, please go back to figure 20A. This is my psi AD, right. This is nothing for you. This is for my reference, right. So this is psi AD. Psi D is equal to minus LLID plus psi AD. Go to figure 20, I think figure 20A, right. Similarly, figure 20B, that psi q is equal to minus LLIQ plus LAQS into minus IQ, right, or it is psi q is equal to minus LLIQ plus psi AQ. This is actually psi AQ. This is equation 239. You will go back to figure 20B, right. Now therefore, psi FD is equal to LADS bracket minus ID plus IFD plus LFD IFD, all you go back to figure 20A or B, right, and or psi FD is equal to psi AD plus LFD ID, because this term is psi AD, that is equation 240, right. Now psi AD and psi q are the air gap, that is mutual flux linkages, and LADS and LAQS are the saturated values of the mutual inductances, right. From equation 240, I mean from this equation, just previous equation, we can write IFD is equal to psi FD minus psi FD upon LFD, right. So this is equation 241. This is for my own reference, right. Now the dx is mutual flux linkage can be written in terms of psi FD and ID. Therefore psi AD can be written as minus LADS ID plus LADS IFD. I mean just multiply that this equation just this equation is minus LADS ID plus your LADS IFD, right. I mean this is your psi AD, this is actually somewhere this is actually your psi AD, this is psi AD, it is psi AD is equal to minus LADS ID plus your LADS IFD, right. So now therefore your this is minus LADS ID and IFD from this equation, this one you substitute here, right, you put it here. So that means psi AD is equal to written as LADS dash into bracket minus ID plus psi FD upon LFD. Say this is equation 242, right, where LADS dash is equal to 1 upon your denominator 1 upon numerator, denominator will be 1 upon LADSS 1 upon LADS plus 1 upon LFD. This you just simplify, you will get it, right, just you simplify. Since there are no rotor circuit considered in the Q axis, the mutual flux linkage is given by psi AQ is equal to minus LAQS IQ. This we have seen, this is equation 244, right. Therefore, the air gap torque is, we know this equation, T is equal to psi D IQ minus psi Q ID. This is the air gap torque, or we can write T is equal to psi A D IQ minus psi AQ ID. This is a small exercise for you, that we are writing T is equal to psi D IQ minus psi Q ID. This we have seen before, is equal to, we are writing that psi A D IQ and psi AQ ID. This is a small exercise for you, that this one and this one, right. Why we are writing like this? This is nothing for you, and this is also nothing for you, right. This is a small exercise for you. Put the answer in the forum. If you can't do it, we'll explain there, right. So, 1 or 2 I am leaving up to you. Just all these derivations have been made before. So, from that we are writing like this. So, why we are writing like this, right. So, just hold on, we will go to the next page. So, with the p psi terms and speed variations neglected, the stator voltage equations are. So, you go back to that your stator voltage equations, whatever have been derived much before, right. There what you do, you with p psi terms and speed variation you neglect and rewrite those equations for ED and EQ, right. So, you with p psi terms and speed variations you neglect, and the stator voltage equation, then you will find simply ED will be minus RAID minus psi Q. Just you go back to the stator voltage equation and drop those terms. It is simply like this, and your ED will be minus RAID and psi Q will be LLIQ minus psi AQ. This is again, it is coming from figure 20b. This psi Q is equal to LLIQ minus psi AQ. This is figure your 20b, if I recall correctly, and just or just see the previous equations whatever have been made, right. So, this is actually equation 246, or similarly EQ is equal to minus RAIQ plus psi D, and this is again this psi D is equal to LLID minus psi AD. This equation again from figure 20a, just go back to that, right. Therefore, EQ is equal to minus RAIQ minus LLID minus psi AD. This is equation 247, right. So, now with referring to figure 26, the machine terminal and infinite bus voltage in terms of the dx and q axis component are, this we have seen in figure 26, the ET tilde is ED plus JQ, this is 248, and EB, that your what you call, there are two components are there, direct axis and quadrature axis component. So, it is EBD plus JEBQ. Please go back to figure 26 and you can get it, and you can easily see this, right, already I have told. Therefore, network constant equation for the system of figure 23b is, right, that is ET tilde is equal to EB plus RE plus JXC IT. This is actually, you go back to figure 23b, figure 23 was that your generator, then a transmission system, then a loss system, and Thevenin equivalent was that RE plus JXC, and in addition to that and the infinite Thevenin bus voltage, that is Thevenin voltage EB, that is given only on your figure 23b. So, from that thing your figure you can easily write ET tilde is equal to EB tilde plus RE plus JXC IT tilde, right, or ED plus JQ, ET tilde is equal to ED plus JQ, EB tilde is equal to EBD plus JBQ, and RE plus JXC, and IT tilde is equal to ID plus JXQ, right, and this is my equation 250, right. Now, if you multiply and you separate real and imaginary part, then you will get, you just multiply and simplify and separate real and imaginary part, you will get ED is equal to REID minus XCIQ plus EBD, capital EBD, this 251, and EQ is equal to REIQ plus XCID plus EBQ. This is equation 252, right. That means, this one you put all these things, you multiply this one and then separate real and imaginary part, right, you will get this equation. Thank you very much, we will be back again.